In this video, we'll be looking at null and column spaces, which are subspaces of vector spaces coming from, respectively, the kernels and images of a linear transformation. Given any map between a pair of vector spaces, we say that the kernel of this map, which we'll call often K or kernel of our map F, is going to be the set of all vectors inside V such that f of V is the zero vector in W. So this is pretty much everything that's going to map to zero. In a general map, you guys might have seen this for something like the real numbers before. If ever you had a map, say f of x is equal to, 4 minus x squared, this is not a linear map, but it is a map from the reals to the reals. The kernel of this is the points plus and minus 2. So it's just some set inside our range. The image of a function, which we may call I or image of f, is the set of all vectors W inside W, so that there exists a vector V inside V such that f of V is equal to W. So for this same map that we see on the left, the image of f is every real number less than or equal to 4. So this is the set of all reals from negative infinity up to positive 4. So note that this is a map, F was a map from R to R. In many of the examples that we're about to see, our two vector spaces might be different. So for an arbitrary, for example, linear transformation that we'll consider, so instead of calling these F, let's stick with T. When we're going from some, let's actually stick with real vector spaces for a moment. If we have a matrix, an n by m matrix, our two vector spaces, V and W, we'll be really interested in looking at what these kernels and images are for linear transformations, as this is a natural way for us to generate classes of subspaces. So for the previous example that I gave you to show you kernels and images, we actually looked at something that wasn't a linear map. So let's go back and look at maybe a map T that'll take us from R3 to R2, where our map will take in vectors, let's say v1, v2, v3 is our vector with 3 coordinates. And the map down to R2 I'm going to choose is 2v1 plus v2, and maybe 3v2 minus v3. So this is a linear map that could be represented by the matrix. So our map, let's just call it A, would be represented by the matrix, the 3-2 matrix. It'll be 2, 1, 0, and 0, 3, negative 1. So the kernel of this map T is going to be the set of all vectors in R3 that map to 0. So a quick examination of this, we see that V1 should be equal to negative 1/2 V2, or maybe in the other direction. Given some arbitrary choice of V1, if we made V1S, we know that V2 would have to be negative 1/2 or negative 2s. And v3, given plugging this in for v3, we'll see this is negative 6s, so v3 would have to be positive 6s. So the kernel of our map will be all vectors of the form s, negative 2s, and 6s. So this is the set of all such vectors. I should make this look a little more like an s and less like a 5, such that s is any real number that we choose. So you note once I specified what my vector v1 was, or what my coordinate v1 was, that forced the equations 2v1 plus v2 is equal to 0 and 3v2 minus v3 is equal to 0, since we wanted to look at for what choices of v1, v2, and v3 do we get the 0 vector in R2. Solving this system of linear equations, we see our kernel is of this form. Similarly, we might be interested in looking at the image of a given set. So let's take the linear transformation, this time from R2 to R3. So this will be a completely different transformation, where let's say we're going to take in, let's go with v1 and v2, and we'll output 2v1 plus 3v2, 2v2, and negative v1. So this would be represented by some matrix A, just going down a rows. This is now a 3x2 matrix, where it'll be 2, 3, 0, 2, negative 1, 0. So this will be our map from R2 to R3. Looking at the image of this, we see that it's going to be all vectors of the form, of this form given. So our set of vectors we can get as the span of the two vectors in this column space. So 2, 0, 1, negative 1, 3, 2, 0. Given like any element, we'll call this the span, is actually equal to the image of this transformation T, given that any vector W that's inside our image must be of the form 2, 0, negative 1 times some parameter s. So this is whatever v1 I was plugging in, plus 3, 2, 0. Oh, sorry, 3, 2, 0 times some parameter t. So these are our choices. So this is for any s, t, and r. This is exactly what would put something inside our image. So you might notice that the way that we constructed our kernels and our images of these linear transformations had to do with the structure of the corresponding matrix that we were looking at. So let's see how we can use MATLAB to do this a little faster. When we're working with linear transformations of vector spaces, we actually use special terms for this kernel of our linear transformation T and the image of our transformation T. So namely, we call these things the null space, or null, of typically we actually, we'll look at the associated matrix A coming from our linear transformation. We call this null A and call A. So these two respectively refer to the set of all vectors V inside our original vector space, so that T of V is equal to the 0 vector, or equivalently, if we have this A as our matrix of this linear transformation, this is our V and V, so that AV is equal to the 0 vector. For the column space, in the same way that for a matrix A, we were able to actually construct the image by looking at all linear combinations of the columns, we say the column space of A is the set of all vectors W inside of our image, inside of the codomain of our function, so that t of w is equal to, that t of v is equal to w for some v in w, or alternately, again, putting this in terms of the matrices, this is the set of all w, so that there exists a v, so that a v is equal to w. And an alternate way of phrasing this is the span of the columns of A. So if we write A as a matrix with columns A1, A2, let's put these as vectors, A, M, this is the span of the set A1, A2 through AM. Let's see computationally what we're going to do. So if we wanted to actually find the null space of a matrix, our goal, if we start with, let's say, this matrix A here, is to calculate the null space. Our first step is going to be to row reduce A. All right, if you look, I've entered our matrix A into this, so let's actually run both our matrix A, so let's run in advance. Our matrix A is that same one that you saw on screen a minute ago, and our row reduced form of this matrix is 1, -2, 0, -1, 3, 0, 0, 1, 2, -1. So I'm going to go put this over onto our slide so that we can see how we can use this to calculate our null space. As you can see, I've transferred our row reduced A into our slide. So looking at this, the way that we're going to calculate our kernel is we know that we actually are just going to go through and look at all of our different free variables, which in this case, our free variables are our second coordinate, our third, and our fourth coordinate. So these are the three variables that this is going to correspond to. So our kernel inside of this space, we can actually pick any three parameters that I want. So I'm going to call them maybe T1, T2, and T3 for each of my free variables. And for my basic variables, so we're going to call this maybe x1 and x3. We know that x1 can be written as 2t2 plus 1t4 minus 3, should be careful with how we use these. So t1, t2 minus t3. So those are our three free variables. We could also call them like x, y, like any sort of three free parameters that we want. My x2 is this parameter t. My x3 is not a free variable, it's a basic variable, so we'll look at, we can write him as negative. This is our t1, t2, and t3, just to make sure we see where our parameters are coming from. This is going to be negative t2 plus 2t3. X4 is a free variable, so that's t2, and x5 is t3. So every element inside our null space will be of the form null of A looks like vectors of the form, make this big, 2t1 plus t2 minus 3t3, t1, negative 2t2 plus 2t3, t2 and t3, so there's our set. It's a very terrible parenthesis for any t1, t2, and t3 inside our whatever our field is. So in this case, we're going to be looking mostly at R. So our null space, looking at, we'll again come back to this later, because we have three free variables, we're going to say the dimension of this null space of A, since there are 3 free parameters, there's 3 dimensions of things that are being sent to 0. So these are all of our solutions to the matrix AX is equal to 0. So one of the nice properties of null spaces is we can actually immediately identify whether or not a matrix is invertible by looking at what's in our null space. Namely, if we have a square matrix, meaning our map, the transformation this corresponds to is a map from, let's say, a vector space Rn to itself. So this is an n by n square matrix. If our Rn over here is mapped to Rn, and the only thing on this side that maps to 0 is the 0 vector, that's essentially told us a lot about the structure of these maps. The only way that we would have more elements in our null space is if the image of our map on this side, which still is going to include 0, if this is going to map down to some smaller subset of our original set. So our 0 vector is still certainly going to be in there, but getting other non-zero vectors will actually make it so that our matrix can't be invertible. So this is an additional property that's going to allow us to identify invertibility or not, is if the only vector that satisfies, let's maybe stick with A for this one, the only vector satisfying AX is equal to 0, if and only if x is equal to 0. So if this holds, then that means that A inverse exists. Another reason that we care about null spaces is a null space is a subspace of our overall vector space. And the way that we can see this is we can just show that it satisfies the property of a subspace, namely closure under multiplication by R and closure under addition of elements in our vector space. So to restate that, remember that W is a subspace if 1, given any x inside R, given any, let's maybe stick with C's, given any constant inside our field, any scalar multiple of a vector is also inside that subspace, and 2, given any W1 and W2, both inside our subspace, we want W1 plus W2 to also be inside our subspace. So let's just show that null spaces have to satisfy this property by definition. So suppose, let's say, our proof, suppose for 1 that W is inside the null space of a matrix A. Then we know that A times W is equal to 0. So C times W is A times C times W. We know one of the properties of matrix multiplication is I can multiply by a matrix, then a scalar, or multiply by a scalar and then a matrix. So a multiplication by A commutes with multiplication by a constant. So we can rearrange this way. And we already know that A times W is Z, so this is the same as C times the 0 vector, and any constant times the 0 vector is the 0 vector. So property 1 holds. For our second vector, suppose both W1 and W2 are inside our null space of A. By definition, that means that AW1 is equal to AW2 is equal to the 0 vector. So if we look at A times W1 plus W2, that's the same as AW1 plus AW2. So matrix multiplication distributes over vector addition. So we know that both of those individually are 0, so their sum should be 0. So property 2 holds, therefore null of A is a subspace. Sorry, is a subspace of R to the n. This is a good place for us to stop this video. In the next video, we're going to come back and examine equivalent properties for column spaces.